The next part I'm going to talk about is, talking a little bit about the fundamentals of remote sensing. We have a different definition. This following tutorial is information that I obtained from the Canadian Centre for Remote Sensing. This is an example of a remote sensing classification done way back in the old days. This is from a dot matrix printer. And actually, GIS, if you don't know, in Mongolia was started by a Canadian, I think Tomlinson was his name. A Canadian researcher actually invented the concepts of GIS that we know today. So he's what we call in North America the grandfather of GIS. Not as the Americans would like, the president of ESRI. We'll break down remote sensing process into a number of components. Okay? There is basically 7 components. So the first thing, of course, is the energy source, so the illumination, which is the sun. Okay? So you have basically radiation from the sun. It comes through the atmosphere and it hits the ground or hits an object. Okay, and if you did we did the GNSS course or the GPS course, you realize that same issue with atmospheres. Obviously, atmosphere will interfere with the radio waves. Okay, I use the word radio in equivalent to electromagnetic waves, radio waves. So some of that radiation or energy source hits the ground, and some of it bounces off. Some of it is transmitted into the ground and absorbed. And the reflected radiation is what is sensed by the satellite. And in some cases, the satellite transmits the results back to the ground station. And sometimes the ground station is not within line of sight to the satellite, so the satellite would bounce it off another satellite to the ground station. So these are different ways it sends the information back to the ground station. And then once the ground station receives and processes the data, it forwards it on for interpretation and analysis. So the remote sensing lab would do some initial interpretation and analysis, and then it would make it available to you to use on the application. So then they had to put it online, and then you go to the website, download the image to process, or you buy the CDs or DVDs like it's shipped to you. Okay? So whatever we do is basically a result of this process. Yeah? So in the case of drones, you replace D with a drone instead of a satellite. It could be a plane, a drone, or a satellite. Yeah? That's basically a radio wave, electromagnetic radiation. We use the same word. Radio waves have an electrical field and a magnetic field, so that's all you have to worry about. It is defined by wavelength. So wavelength is that's one cycle. You get long waves and you get short waves. And then you get hertz, cycles per second. So how many times, how fast, how many cycles of this wave goes past this line in a second is your hertz, is your frequency. So those combination is in a radio wave. Okay? This is the spectrum. This is what we're working with in remote sensing. So you got here, to give you an idea, you have wavelengths as long as 1 kilometer, very long wave. You have nanometer, and 10 to the power minus 12, so very short waves. And then so basically your FM radio, AM radio, the radio waves that we hear, the music is up in this band. They're the long waves. And then here is the microwave. So after radio wave and microwave, so some of the transmission, you transmit information through microwave. And most of the remote sensing, we kind of work in this area, between infrared and ultraviolet. And this area is kind of the dangerous area, the really short ones. It's like X-ray, when you go get X-ray your body at the hospital, that's the waves. And this is gamma waves. This is, if you have a nuclear war, that's the waves you get to kill you. What our eyes see is very little. So out of all the electromagnetic waves, we have very limited window of view for our eyes. But we have tools and equipment that will allow us to move from the infrared to the ultraviolet that we can use, and we can use the instruments to simulate what we can see. Then now we're talking about the target. So when the light hits the target, so certain things happen. So the light that comes from the sun is what we call incident light. And then when it hits the leaf, for example, some of the light, the incident light is absorbed. And then some of the light is transmitted, goes through the leaf, goes past some of the waves. Okay, and then what is left is reflected. If eye is everything, some of it's absorbed, some of it goes through, the rest comes back. The reflected light, there's two types, what they call specular and diffuse. So specular, let me explain it. Specular is the reflection is very direct. It's like looking at a mirror, coming off a mirror. So a mirror perfectly reflects the light back to you. Okay? Something like a tree, what we call diffuse is if you put a film over the mirror, then it diffuses the light. Well, instead of a very sharp picture, it's a little blurry, out of focus, because the light is spread out. Okay, so that's the two extremes. Somewhere in between is what is real life happens. Okay, very diffuse, very direct, and then in between. Okay? In terms of plants, okay, so the tree normally, okay, these are the different frequencies of the wavelengths: infrared, red, green, blue. If this is the band of light coming, incident light contains all these wavelengths. The tree basically will absorb blue and the red, and it will reflect the green and infrared. So the principle here is this is just an example. Most objects reflect differently, and that would affect what you see, what we see in the little band, but there's a bigger wavelength. But anyway, so depends on the target, what the target is. A wheat field versus a forest, you'll have different types of frequencies being reflected. Between a forest, pasture land, and a lake, they reflect light differently and absorb light differently. Okay, so for example, water will absorb the infrared and the near infrared more than the blue and the green. So when you look at a water body, the blue comes back to you. It's reflected. That's why when we fly over the ocean, it looks blue, because the blue light is coming back, everything else seems to be absorbed. I'm trying to show this example. This is clear water in the lake. The blue will come back. If you have algae or sediment, then more green will come back. Yeah. So if you're doing photo interpretation on the quality of the lake, the reflections will tell you one lake is good and healthy, the other lake has too much algae or sediment, because the colors will be different. Okay, so in terms of sensing, there's two types of sensing mainly. There's what's called passive sensing and active sensing. So passive sensing is if you're just sitting there waiting for the light to reflect from another source, like the sun. Sun's shining, you see it, you get the waves, that's passive, you're not doing anything. So active sensing is the satellite actually sending radio waves down directly. It is actually sending a light beam down and then getting it back. That's active. So, okay, passive satellites have to be in daylight. When it's on the other side of the Earth, you can't set, there's no light, okay? Active sensing, you can do it 7/24. So I'll give you an example of active sensing. In Canada, in the east part of Canada, in the Atlantic Ocean, we have issues with icebergs in the winter. Icebergs, or spring, I guess, spring. Icebergs break off from the Arctic and it flows into the Atlantic. And we have ships coming to Canada. Well, the Titanic, that's an iceberg. Huh? So the problem with trying to spot icebergs using satellite is cloud cover. So usually you have cloud and you can't see the iceberg. So the Canadian government supported the development of radar sat. The radar sat is basically an active sensing radar It uses microwave, it penetrates cloud, and it can spot icebergs. So it can warn the ships that there's iceberg ahead because it can see it. Now the spin-off from that is, always this value added, like in the private sector, there's value added. When the government does it for something, then we use it for other things. So RadarSat has developed to be able to actually do black and white, topographic mapping in the rest of the land, on the land side as well. We can boil down remote sensing into little squares, and little squares with numbers. An image is a pictorial representation, regardless of wavelength, a record of electromagnetic energy. And a photograph are images that has been recorded on photographic film. And a photograph has a limited wavelength of 0.3 to 0.9. So a remote sensing satellite can capture images at a very wide band of wavelengths, wider than the visible. Anyway, so with the satellite, it can capture, depending on the sensor, it can capture wavelengths different than we can see. Okay, more than we can see. All right? But in order to let us see it, what they've captured, even though it's outside our visible light, it actually converts the information into numbers. And we use those numbers back into, say, grayscale, okay, that our eyes can see. So basically, it's a wavelength that we can't see. It interprets it into numbers. And we take the numbers and we put it into a scale that we can see. Part of the interpretation exercise at the station, at the receiving station. Channels and bands. So if this was a satellite image and you had two bands, the interpretation coming back will give you different information in those bands. That could be, say, infrared, and this could be color, We can't see infrared, but what the machine does is say, based on the infrared wavelengths, if we do a histogram, we spread it out, that's what it shows. We have more or less three kinds of satellites. We have geostationary satellite. That means it doesn't move. It stays on the same place. GOES goes. The weather satellite is geostationary. Then you have the what we call near polar orbits. So satellites that fly around the pole, the north and south pole. And basically your description of ascending and descending paths as it goes around. We'll talk about swaths maybe in a revisit period. So the satellite, the sensors on the satellite would cover a certain width. It could be 1 kilometer, 5 kilometers. That's called a swath. We use the word swath as like farmer, with the combine. You cut a swath in the field. That's a swath. Okay. So the nadir is the height of the satellite above where it's taking the image. The nadir for the geosynchronous satellite is 36,000 kilometers. So these are the swaths, for example, of a satellite. Okay? Over one pass. Some of them would overlap later. So eventually, I assume that they will fill out all the yellow. Either the swaths move over, then eventually it becomes all yellow over time. Okay. Or you need 2 or 3 satellites to cover all the areas. Some of the commercial satellites, you can actually program it to go fly, to take an image where you want it. Spatial resolution, pixel size, and scale. Spatial resolution is defined by the height, the camera area of the ground, or the focal length, coarse and high resolution. So depending on the camera, the height, you could get coarse or high resolution. So each pixel is much smaller distance than the pixel. Right? Okay, so like their flight was 67 centimeters pixel. Our flight was 5-6 centimeter pixel. Okay, so 10 times more resolution. So resolution is important because if you remember when I was doing Africa, I was trying to look at roads and I had only Landsat at 30 meters, I could not find the roads because it's too close. So there is an optimum size though, right? If you, in my case, that's, in Africa, it was not fine enough for me, right? In Afghanistan, the American military gave me 4 centimeter imagery to do my drainage canal. It was too fine. I only needed ½ meter. So basically, to go from a ½ meter to 4 centimeters, I don't know. It was gigabytes of raster imagery that I could not process on my laptop. So ideally, we would like an image that has the right pixel size for us to do our work. Spectral resolution. This is a little. So we got image resolution. Now we got spectral resolution. If you have black and white film, it actually covers a range of 0.4 to 0.7 because blue, green, and red is just one shade in black and white. So 3 bands of light, red, green, and blue is all one in black and white film. So the only way we look at the image is grayscale, right? Dark to light with black and white. So if I was doing photo interpretation just with black and white film or panchromatic film, all I got to tell between one object and another or one class and another is grayscale. But if I was using color film, I actually have 3 layers. I have the blue layer, the green layer, and I have the red layer. So go back to black and white film, I have 1 layer. I can go from dark to light. If I have color film, I can separate it out into 3 layers. Each layer has different dark to light densities. So if I was using this to do multi-spectral analysis, I have more combinations to separate out the different objects that I want to classify. Then we look at another thing called radiometric resolution. So we got image resolution, we got the light, and then now we got radiometric. So radiometric resolution, this goes back to what we were beginning to say about the range of your remote sensing satellite wavelengths. Okay, so there are wavelengths that the eye cannot see, that the instrument, the sensor can pick up, all right, like the red, green, blue in color. And you can store the data. So in the old days, because memory was a problem, the first images actually was only 2 bits, which is 2 to the power of 4. You can store 16 shades of gray. I'm going to say 16 shades of gray. What was the movie? Right? If you had a 2-bit sensor, right, you can only store 16 shades, 0 to 15 values. So it's like, so if you have less, the palette is less, right? So 16 shades of gray is not as nice as 256 shades of gray, right? For example, I think this is 2-bit, and this is 8-bit, okay? So this is more white, these are gray shades, okay? But temporal resolution. So temporal resolution is another resolution we talked about. You remember the swaths, and I said, if I'm standing here, the satellite comes over, the next time it comes over is the difference in time, the tempo, okay? So in some cases, you would like it to come more often, but depending on the satellite, if it doesn't come in 2 months, maybe it's too late to get the difference. So temporal resolution is important. It's the frequency of the satellite coming back to the same place to take another image. Okay, let's say that lady is doing flood studies, right? So we have the satellite over when the flood is occurring, and maybe there's some clouds, and so she would like some images taken. So the next time the satellite comes over, it might be 18 days later, the flood's gone. So it's important in some cases, to have maybe the satellite come back in 2 days or 3 days rather than a month. So it'll affect your research. So back to the camera. So for cameras and aerial photography, then basically you have an area A that is given by the lens, the focal length, and the focal plane. So I think we talked about the pixel scale, that's the same idea here, okay? So A is captured in C. So the sensor in C, the more pixels, the better the resolution will be for the ground A, the image you're trying to take of A. The more megapixels you have in C, the better the resolution in A. Color and false color. Color is red, green, blue. False color is usually simulated color using, I think, near infrared. So false color, I believe, picks up trees, I think the vegetation better than in red. So multi-spectral scanning. So this is now satellite scanning. There's two types of scanning. One is basically like a TV, first one. It's like a TV, the sensor starts here and moves across and it picks up the image like a sweep, like a broom. Okay. So that's one sensor. The other one is an array, so you have a whole row of sensors and it takes it all at the same time. GOES, which is your geostationary, that's a satellite that doesn't move, it stays in the same place. That is Florida on the left, so that's a hurricane. And so it's 3,600 kilometers above the Earth in orbit, fixed orbit. And I believe there's three of them, they're roughly 70 degrees longitude apart. Now if you think about it, it's 360 degrees, 70 times 3 is only 210, so there's a big chunk of the Earth they're not interested in. So the GOES band, 5 sensors in the GOES. Basically, you have the visible, 1 kilometer resolution. It looks at cloud pollution, haze detection, and storm identification. So band 1. So the second one is shortwave infrared, which allows them to look at fog, water clouds, snow, ice during daytime, fires and volcanoes, and determine the temperature of the ocean at night. You've seen pictures of El Nino and El Nina, where the ocean color, the temperature of the ocean moving around. That's probably generated from this band. Okay. And then the third one is for water, upper level water vapor, moisture content, okay? And for researchers looking at advection. For example, forests in Brazil, you know, how much moisture is leaving the jungle. So band 4 is long wave infrared, clouds, storms, and rain. And then this one is really band 5 is an area low level moisture, determines the sea level, certain temperature again, airborne dust and ash. So a lot of this is related to atmospheric pollution and water temperature. This is the NOAA, the weather people, and the AVHRR is basically the advanced, very high resolution radiometer. And like GOES, NOAA has basically 5 bands, but in the case of NOAA, they're all around 1 kilometer pixel. Okay, I won't go through each one, but essentially NOAA is dealing, the wavelength is red, near infrared, mid infrared, and thermal. And I believe the Institute uses NOAA for some of the work that it's done here, for some of the classification, the big scale, Mongolia-wide. And I think NOAA data is available from the Environmental Information Center, yeah? So some of the formats, so these are the outputs. So you go back to the 4 kilometers and the 1 kilometer. So low resolution direct transmission. So if you're downloading the data directly, the satellite's 4 kilometers. Okay, so the other one you can also get direct is the 1 kilometer, but that will take probably more capacity. So and then same thing with recorded. So you can also get recorded from global, and you get local at a lower resolution, but global you get at 4 kilometers. So you get it from the Americans. So some of the usage of NOAA data, for example, is when you do countrywide remote sensing analysis, you would use the very high resolution imagery. So that's, I think, wheat. So then we come to Landsat, and we already covered Landsat earlier. So you have the first Landsats up to 4 and 5. You have basically 7 multispectral bands. Essentially, these are in different bands, but they're collecting the information. Like on the Landsat 1, 2, and 3, band 4 is the same as band 1 in 4 and 5. So really, that's 0.5 to 0.6 is the wavelength. So as you increase the wavelength, then you go from green to red to near infrared to another band of near infrared. So the thematic bands then, if you look at the channels, you have basically the frequency, the wavelengths keep increasing as you move on this way. So blue, green, red, near infrared, shortwave infrared, and thermal infrared. So in terms of what you use it for based on refraction, the blue is good to classify soil vegetation, bathymetry, coastal, water, and then green is for vegetation mapping. So you see it measures the reflectance from the plants. And the red separates the vegetation from the non-vegetation. Okay, so in other words, in the urban areas or in the soil versus vegetation. Discriminates between plant species, and some plants would absorb more and others won't. Okay, so there's the difference based on the chlorophyll. And in the near infrared, you can go everything from plants, plant health, odor body, and soil moisture. Thermal infrared will tell you what plants are in trouble, if you know. So the farmers, okay, if in Canada we have big farms, and so the farmer wants to know, if certain parts of his crop is under stress, so he'd probably look at this band. And then if you're doing, I guess, for mineral and rocks, you may be looking at band 7. You can play around with these with multispec if we can get some imagery to play with on Monday. So in Canada, we have a lot of forests, especially in the north and in the west. So we have this very bad practice called clear cutting. The forest companies go in and they just cut all the trees. Okay, so you can kind of tell. Although I think that practice is kind of changing slowly. If you drive through Canada, you could still see chunks of forest gone. So we're talking about temporal, like time. So the time that was done in 84, this is done 91. So basically you have 7 years difference, yeah? So you can see the changes over 7 years. So then we come to the commercial satellite. So like SPOT. I think SPOT is quite popular. And most of the SPOT imagery is around 10 meter resolution, but the multispectral is 20. This is just showing you the same image we saw earlier, because the satellites can send the information down directly to the receiver station. And where it's not possible, they would transmit through another satellite. So now I come to image analysis. So assuming that we're now receiving the data from the satellites, you have 4 steps, yeah? Pre-processing, image enhancement, image transformation, image classification and analysis. So usually pre-processing is done at the satellite base station. So they try to clean up some of the data, okay? If there's some noise in the image, they remove it. Sometimes they do some enhancement of the imagery, but usually I think the user does more of the enhancement than the vendor. And definitely it'll be the user that does the classification and analysis. Yeah? Some idea of enhancement. So supposedly the enhancement is like when you take digital photos and you take it into Photoshop or something, and you don't have enough light, you enhance the image. You do the same thing with satellite. So one type of transformation is, if you recall, when we looked at the panchromatic, covers 3 bands. It has a limited grayscale, like you might have just grayscale for black and white, which covers all the visible light, all red, green, and blue. Yeah? And then you have basically the color where you have 3, red, green, and blue. Each one has an image, okay, and you could do different things with that. So that's called transformation. So supposedly, for example, this is the red image, the green image, and the blue image. You can do a transformation and create a composite image based on the 3. So you can merge the 3 to make 1. And you can choose to accentuate one layer, one color versus another, or you can combine 2 to make 1, and then the other 2 to make 1, okay? So there are different combinations for you to determine what gives you the best results of what you're trying to classify. Okay, and the other thing you do in transformation is geometric registration, or georegistration, or georeferencing. Suppose this is north, okay, north, south, east, west, okay? Now the swath, the satellite flies across the Earth this angle. So you get a picture, JPEG or whatever, TIFF, it's cube. So you need to change the coordinates to fix it. So you need ground control points, okay? And then you register them. Just so that you know, if this is the corrected image, that pixel is close to this pixel, but it's not quite, right? So it's overlapping. So it actually has to recalculate. Say the satellite image pixels go across this way and down this way, all right? We want the pixels to be lined up to our UTM coordinates. So what happens, for example, this pixel here has to be transformed to here. And sometimes, you need pretty good mathematical, by cubic spline, and all that kind of stuff to actually get the best transformation. So that being said, when we process images, all right, it actually degrades the actual information a little bit. So you have to be aware that the raw image from the satellite transform is slightly degraded. And depending on what you're doing, you might be better off to classify the unrectified image first and then actually transpose the vector later. That might give you better results. I'm just saying, depends on what you're doing. You might sometimes be better off to do the classification on the unrectified or unregistered image, get your polygons, and then transpose the polygons. Then to transpose the pixels, and then classify the pixels. To say this another way to make you even more confused, right? In the original image, this pixel may say, let's have a number of 232, okay, value. When you do the mathematical algorithm to twist these points, it may end up here as 232, 228. So all those numbers change a little bit. Yeah, and then depending on your analysis, it might fall out instead of falling in. Okay, something you're looking for. Okay. So what does image enhancement mean? You get an image like that. It's hard to see, so we want to enhance it to this image. It's better for us to see and classify. So what it's telling you here, this example here, if this is the histogram of the image. So as we said, that each band you have, if it's an 8-bit sensor, you have a value of 0 to 255. As an example, the histogram goes from 84 to 153, so it's kind of narrow. If we enhance this, what they're doing is they're taking the two endpoints, so it's 84 and 153, and they're stretching it. So they want to use the whole range of the color, rather than just a small range. This is not exactly what's happening there, but that's the idea. So transformation, as I've said before, you're taking multiple layers and manipulating them to create an output, a different layer. We have this layer and this layer. We want to subtract this information. So it could be subtract, it could be add, okay? So it depends. So you use image transformation, for example, to look at the vegetation analysis in Canada. It's actually worth noting, if you're interested. The green means it's good, but good crop, okay? So you can see that Ontario, Quebec has pretty good agriculture. And then in the middle of Canada, we have Manitoba. It's also pretty good around Winnipeg. And this is Alberta. Alberta actually has some pretty good vegetation up the middle of Alberta. And then this is British Columbia. The Fraser Valley, that's also an extremely good agricultural area. But it's worth pointing out, Saskatchewan is very dry. And you can tell that, the crops there is not so good in the south because there's not enough water. And obviously up in the Arctic, too much permafrost up here. On the left, they're trying to show you kind of a classified example. So if you knew that this is water, here, you say, okay, I can classify that as water. And I know that this is agriculture, and I know that this is rock. I can classify these. I put this over here, and I say, okay, whatever's in this pixel, it should be water, whatever the number. And whatever numbers in this pixels should be agriculture. And then over here, it should be basically rock. So this is what we call classifying, okay? So when you process this information through the different layers, you end up with a total picture that the remote sensing tells you this is all water, which matches this part is also looks like it's water. This is all agriculture, and this part is rock. If you want to go into more detail over here, this is looking at color pictures, which you do in multi-spec, and looking at the image from the visible. But mathematically, what happens is you're saying this area is water. So guess what? Water looks like it's in the 10 to 14 number of water. So when you say this is water, and the machine looks at the area and says, okay, the number here of the 8-bit scanner sensor is all around the low 10s. Anything that's 10, 11 to 14, they would classify as water. In agriculture, we can see that agriculture is really in the 80s and 90s. So the software will go through and say anything that's between 80 and 90, we'll say it's classified as agriculture. A rock has a value in the 170 to 180 value. Okay, so based on those numbers, the software can then create a map and give you this output. But that's an example. In real life, it's much more complicated than this. It never works quite as nice as. So anyway, as an experienced remote sensing person, as you work on this, you will become more familiar. What is the best bands for you to use to look for certain things? And then you can use combination of bands to try and segregate the numbers so that they come out like this. Data integration and analysis. So what happens in real life when you do a project is multiple information that you will be using. You may be using Landsat data from 95 to 97, those series. You may also have basically other images at different resolution, from high to low resolution. And you may have additional aerial photography. Okay. And you may have maps from other people with other digital data. When you want to work, then you need to put all this stuff together, integrate. Which brings me back to geodesy and an understanding of coordinate systems, because this information has to line up on top of each other or you're going to get garbage. And so, in my experience, when I do projects, I will find data that is good but doesn't fit, and I cannot make it fit, and I have to throw it away. So it is kind of important that, if we're working together, that we keep the metadata so that people understand, how good the information is, all right? And sometimes you may have a very beautiful map and good metadata in terms of the projection, but you don't know how the person generated that map, how good the information is on the map. So it may be a classified map, but it may be, because when we go to digital, we no longer have mapping scale, right? There's no scale when we go digital. So somebody may have digitized a 1 to 1 million scale map and give that information to you. All you see is the vector data, and the vector data you can plot at any scale. For example, if we take a geological map of Mongolia, not paper, now vector. Suddenly these boundaries look very accurate and very nice. You think it's really good, but the line could be plus or minus 100 meters. Okay, so if you use it in your data and you have low resolution data you did off a drone, which is very accurate, and then you combine it with data that came from maps that were very coarse, and you're mixing incompatible information. Very easily the river on that map digitally could be half a kilometer or a kilometer off. But you wouldn't know unless you knew the metadata from the source where that information was derived from. You would not know that this river is not accurate unless you knew the background. So anyway, that's just a caution. And so that's the end of this part.